Hello, everyone. Welcome to the April 2023 Recreational Astronomy Night meeting of the RASC Toronto Centre. My name is Paul Markov, and I'll be your host for this evening. We are at the Ontario Science Centre tonight in front of a live audience of about 20 people. We apologize for the late start. We had some technical difficulties. To our online viewers, a reminder that we have resumed meetings in person here at the Science Centre, so if you can, please join us next time. For those who definitely cannot make it in person, rest assured that the live broadcasts on YouTube will continue. Thanks to our capable AV team comprised of Andrew and Betty Reed, Ward Legros, Enya Chulucci, and Reza Mohammed. As you know, I'm always on the lookout for presentations for these meetings. In fact, we have one more opening for the May 3rd meeting. If you have anything in mind, please get in touch with me. Future meetings, which occur on the first Wednesday of each month, also have available time slots. Now, regarding the technical difficulties, we were supposed to have 3 presentations this evening, one of them remote. And that was John Percy talking about variable stars. Unfortunately, due to the technical difficulties, we're not able to have John present to us this evening, so we're down to 2 presentations. I'll reschedule John for a future meeting. So the 2 presentations are going to be Arnold Brody presenting the sky this month, and Frank Dempsey, and will talk to us about aurora forecasting. And then we have our president, Tom Luton, to take care of the announcements. And we expect to be done around 9:30. Well, now probably earlier than 9:30 due to the missing presentation, although we are running about 20 minutes late. All right, so if you're watching us online and have a question, please enter it in the YouTube chat box, and Enya will ask the question on your behalf to the speaker here. For in-room questions, hang on and we'll get you a microphone so we can all hear your question. And show of hands, do we have anyone here for the first time? We have 2 or 3 people or so. Yeah, very good, welcome. And for those online, if you are attending one of these meetings for the first time as well, please let us know through the chat box and introduce yourself. So let's get started with Arnold and the sky this month.
Well, thank you, Paul, and hello, everyone here and online. We'll take a look at the sky for the rest of April as it appears from Toronto, and times will be for the Eastern Daylight Saving Time. As we see what's up in the sky this month, I'll suggest a few targets in the sky and on the moon included in these observing programs, in some of them anyway. What you should do is search RASC Observing to find and click on RASC Visual Observing to learn more about these programs and download their observing lists. Lists for deep space objects will include their RA and DEC coordinates, so I won't clutter the slides with them. Now here are some highlights for the month. On April the 8th, we are 366 days away from a total solar eclipse that passes through Niagara, parts of southern Ontario, through southern Quebec, and into Atlantic Canada. Now, that's not exactly a highlight for this month. But who can't wait? I mean, we've been talking about it for years, and now finally on the 8th of April, we will be on the final lap. And yes, there is a leap day in February next year. Now, back to this year, on the night of April 9-10, there's a nice pairing of the moon and Antares. Mercury reaches greatest elongation on the 11th. That same evening, Venus strikes oppose with the Pleiades. On April 14, Mars comes very close to Epsilon Geminorum. New moon arrives on Thursday, the 20th, so Saturday the 22nd is the best Saturday night of the month for deep space, and I'll use that Saturday night when looking at the sky. That Saturday night will feature a lovely grouping of Venus, a thin crescent moon, and the Pleiades. And the Lyriad meteor shower peaks that same night. Friday, April the 28th, marks the kickoff of the 2023 season of public stargazing at Millennium Square at the south end of Liverpool Road in Pickering. Now, there is a benefit, in addition to all those highlights, there's an important benefit in observing the planets and stars in April. The observing window is reasonable in April as suggested by the width of the hourglass in S&T's almanac between April 5 and May 2. Now, I include astronomical twilight with night in what I call the observing window because planets and bright stars can be seen by the time the sun is 12 degrees below the horizon. Now, tonight, the observing window starts at 20:55, call it 9 p.m., and is nearly 9 hours long, and night fills the middle 7 3/4 hours. By month's end, or May 2, the window will shrink by an hour and 23 minutes and night a bit more. The beginning of April sees the moon growing full and washing out deep space targets with the pink moon or breaking ice moon among many names for the April full moon occurring on the 6th. And I should point out that pink moon does not mean the moon is pink. It means that's the time when the pink phlox flower blooms in early spring. New moon finally arrives on Thursday the 20th, making the following weekend the best of the month for deep space. And that date in red, well, that's my second plug for stargazing at Millennium Square that night. Now, let's take a look at that Saturday night after new moon on April the 2nd, or April the 22nd, Saturday, April 22, and a 2-day-old moon is hanging out near Venus as the sun is setting. We'll take a closer look at that pair near the Pleiades later on. At the cusp of night, you have about a half hour or so to catch targets along the Perseus arm of the Milky Way before they are too low and set in the murk, and you can say goodbye till next winter. We can then turn our attention to 3 constellations at or near your meridian as night begins: Cancer, Leo, and Coma Berenices. Cancer is a faint constellation with its 4 brightest stars, magnitudes 3.5, 3.9, 4, and 4.2, which can be a challenge to find in urban glow. To find Cancer, you can probably start with the sickle of Leo and just look to the east about 20 degrees to find these faint stars. The 3.9 star in the middle is Delta Cancri, which lies almost perfectly on the ecliptic. That makes it subject to a series of lunar occultations, with the next new round of those occultations starting in about 4 years. Now, from Delta, slide about 7 degrees southeast to Alpha Cancri. And what happened? There we go. From there, it's less than 2 degrees west to find Messier 67, a rich open cluster that lies 2,800 light years away. Its angular size is half a degree. Now, I'm not sure why, but this is known as the King Cobra cluster. Its 500 to 600 member stars collectively shine at magnitude 6.1. The cluster is around 4 billion years old, and that's about the same age as our sun, and it's one of the oldest open clusters known. And after those 4 billion years, the hottest main sequence stars left are class F and cooler. The rest are red giants off the main sequence, and you may also notice some blue stragglers whose origins are still a bit uncertain. They could be stars that formed much later than their siblings, so they haven't had a chance to go off the main sequence yet. Or they could be the result of 2 stars merging and forming a more massive, hotter star. More than 100 of the cluster's stars match our sun in class and age, so this is a good concentration for those searching for extrasolar planets around sun-like stars. There's an interesting double star in Cancer, magnitude 5.2 Zeta Cancri, a little less than 8 degrees west of Delta Cancri. Its Arabic name is Tegmine, meaning shell of the crab. The two components not fully separated in pairs' drawing. Oh, I'm sorry, I skipped a line. Tegmine is actually a triple star system, as seen in this sketch by Jeremy Perez from 2006. The two components not fully separated in pairs' drawing, those are called Zeta 1, and the other star is Zeta 2. Now, the Zeta 1 stars are orbiting each other. They complete an orbit every 60 years, and they reached their maximum separation in 2020. Now, we are 3 years since max separation, but they should still be easier to split now than they were for Jeremy 17 years ago. Moving over to Leo, we're looking away from the plane of the Milky Way and into the realm of the galaxies. And there's a bright one staring Leo right in the face. 1.5 degrees south of Lambda Leonis, you will find NGC 2903, glowing at magnitude 9. We see the lone galaxy inclined 60 degrees to our line of sight, and it's 30 million light years away. Notice how bright the core is in the middle. Often we will see the center of a large galaxy look a little bit yellowy from aging stars, but we have gas inflowing along the bar, and it has triggered starburst activity. 700 solar masses of stars are being born right in the middle, 2,000 light year radius, right in the very center of that galaxy. 700 new stars a year, which is enormous. Our entire Milky Way galaxy, by reference, only makes 7 new stars a year. So that's quite the starburst activity happening there. Leo is crouched down over 2 groupings of bright galaxies. The first is just 2 degrees below Kappa Leonis, about halfway between Alpha and Theta Leonis. It's known as the M96 group, and in a telescope wide field, you will see 4 of the group's members. Let's see them. Oh yeah, there they are. M95, M96, M105, and NGC 3384. This group lies 37 million light years away. And if you pan around in the neighborhood, you will find more galaxies, including other M96 group members that are marked here. And 2.5 degrees southeast of Theta Leonis, you will find the M66 group, also known as the Leo triplet. It's 35 million light years away, so it's 2 million light years closer than the M96 group. But many cosmologists feel that they are both members of a much larger group. Now, NGC 3628 is nicknamed the Hamburger Galaxy. And that's because there's a thick dust lane bisecting the view we have of the galaxy edge on, slicing it into a sandwich. It's classified as a non-barred spiral, though research hints at a bar pointing straight at us. Bars are common in interacting galaxies, I should say. And the 2 nearby Messier galaxies, they must be hungry because they're pulling on that hamburger. Onto Coma Berenices, which is Latin for Berenice's hair. Gamma Comae Berenices and over a dozen neighboring stars on the cusp of naked eye visibility form softly glowing cascades that in ancient times, up to a couple of hundred years BCE, were often described as the tuft at the end of Leo's tail. But in 245 BCE, when Pharaoh Ptolemy III returned home safely from the Third Syrian War, his consort, Berenices, cut off her long tresses and placed them in a temple as an offering of thanks to the goddess Aphrodite. When the tresses disappeared overnight, Ptolemy, he was pretty upset. But quick-thinking court astronomer Kenan of Samos declared that Aphrodite had accepted Berenice's offering and placed her hair up in the sky, pointing to that hazy cascade of stars as proof. and Ptolemy bought it. He must not have known about the tuff at the end of Leo's tail. And they celebrated. Now, various astronomers through the centuries have kept that story alive in their charts, treating these stars as a separate constellation. And Coma Berenices was ultimately adopted by the IAU, making this the only constellation named after an actual person. The cascade of stars was actually an open cluster hiding in plain sight. It wasn't until 1938 that it was called an open cluster when Robert Trumpler identified 37 of the stars as related. It is now cataloged as Malot 111 and commonly called the Coma star cluster. It has 50 member stars spread over 6 degrees, including many in the 4th and 5th magnitude, like those labeled in this simulated binocular view, but not including Gamma. It's much, much closer to us than the rest of the cluster, which is 280 light years away. Only the Hyades is closer at 153 light years. And the stars in this cluster are 450 million years old, quite young. It's a great target for stabilized binoculars. Now let's turn around and take a look north. April and May are excellent months for observing two galaxies that lie on nearly the same line of sight. Messier's 81 and 82 reach an altitude of 64 degrees when they cross the meridian around the start of night in late April, making this the best time to observe, sketch, or photograph the pair. We're looking through only 1.1 air masses 26 degrees from the zenith. So that means the vision won't be degraded very much at all. To find the pair with 10 by 50 binoculars, you can scan diagonally across the bowl of the Big Dipper from Fecta to Dubhe, then continue for the same length in the same direction, and with any luck, both galaxies are in your binocular field of view. But scanning 20 degrees or so with a telescope, that's difficult. If you're using a telescope, start with Nu Ursae Majoris. That star and the galaxies lie on almost the same line of right ascension. They differ by only 5 minutes. So in other words, the galaxies are almost due north of that star. If you center Nu Ursae Majoris in a wide field of view, you can just scan in declination towards Polaris to find them. M81 on the left and M82 have interacted, resulting in starburst activity in M82. M81 is known as Bode's galaxy. Johann Elhert Bode found it on New Year's Eve, 1774. I guess he didn't have a date. It is a grand design spiral galaxy pegged at 11.7 million light years. Using the period luminosity relationship in Cepheid variables that was identified by Henrietta Leavitt 111 years ago in 1912. The Hubble Space Telescope was used to identify and monitor those variables. The galaxy is bright at magnitude 7, easily seen in any instrument. The narrow appearance of M82 gives it the nickname the Cigar Galaxy. It was also discovered by Bode on the same night, and it's the second starburst galaxy we're taking a look at tonight. It is the closest starburst galaxy to Earth, so it is the prototype and is extensively studied. Like NGC 2903, within the central 2,000 or so diameter from its nucleus, again, 700 solar masses of stars are being born every year, similar to 2903. And the result of that starburst activity is the interaction it had with M81 earlier. Most sources refer to M82 as an irregular galaxy, but two spiral arms were discovered in near-infrared images in 2005, but those are hard to see in optical wavelengths. Imaging brings out enormous red-colored bipolar outflows of ionized hydrogen flying out into intergalactic space. The gas is being jettisoned by the energy of intense solar radiation, solar winds, I should say, from that starburst activity, as well as supernovae explosions. So M82 may not be an irregular galaxy, but it sure looks peculiar. Later into the night, you might like to see what's rising in the east. Here you will see the approach of the summertime constellations. Hercules and Ophiuchus are rising, and the Sagittarius arm of the Milky Way is coming up right behind them. Now, these targets for the summertime will be discussed by those presenting the sky this month at upcoming meetings, but you might like to check some of them out now because there are no mosquitoes, right? Yeah. Now, returning closer to home, let's take a look at our solar system this month, starting with the sun. Watch this circled area in this magnetogram video as it crosses the Earth-facing meridian, when suddenly, right about here, wham, there it is. It suddenly, an active region surfaced so suddenly it caught solar watchers by surprise. As of this morning, the region, now numbered 3270, boasts 15 sunspots. It was graded as a Delta class region yesterday because its positive and negative field lines have concentrated and separated from each other. In other words, you can draw a line between them. When this happens, strong arcs or loops emerge, rising up from the dark blue and plunging down into the red, and that can rip open and produce flares, which can produce auroras or disrupt radio propagation on the sunlit side of Earth. Definitely, this is a new region worth watching. Now, for some reason, the Delta classification was dropped this morning, even though you can still draw a line between the opposite sides of polarity, like I just showed. And the probability of X-class flares has jumped from 1 to 5% today. So I really don't know why they dropped the Delta designation from this. Was it a mistake? I don't know. But definitely this area with those predicted possibility of flares and so on, this is an area definitely worth watching for the next little while before it rotates out of view. Now you can check auroraforecast.com to see the next 3 nights of probability. This is a slide from last year, but you can always visit auroraforecast.com to see what's coming up. And that's just one of many websites out there that can give you forecasts of the possibility of auroras. The number of sunspots for solar cycle 25 has exceeded predictions since the cycle began in mid-2020. The peak is predicted for mid-2025 with monthly counts around 125, but we've already breached that predicted max count with nearly 150 at the start of this year. After a series of underwhelming cycles, number 25 has reversed the trend. The moon this month. The limbs tilted our way by libration are illuminated, so you can try catching the Petite and Glushko craters this week, and the Abel and Helmholtz craters on the opposite side at month's end. Perigee occurs on the 16th, and the moon appears 9% smaller at apogee 12 days later. This is how the moon will look to our guests at the public star party at Millennium Square on Friday, April the 28th. That's my third and final plug for the event. I'm running out of slides. The moon will be 1 day past first quarter, and that's the perfect time to view Rupus Recta, a 110-kilometer fault that stands out when the sun is at just the right angle. The fault looks steep when it casts a dark shadow. Its slope, however, rises 300 meters over 2 to 3 kilometers, a 10% incline. So with a bit of effort, you could walk up this so-called cliff. Rupus recta is Latin for straight cliff, though most call it the straight wall. Further south along the terminator, you can find the central peak in well-defined crater Tycho. That central peak is just reaching up and catching the first sunlight. Throughout the night, the shadow on the crater's floor slowly recedes to the moon's east, exposing more of the central mountains. Tycho is a relatively fresh crater, only 108 million years old, and that's based on samples of ejected material in the crater's rays that were returned to Earth by Apollo 17 astronauts. The crater measures 85 kilometers wide and is 4.8 kilometers deep. The crater's rim is sharp and intact, not broken or worn from subsequent impacts like its neighbors. The walls are slumped and terraced, and the crater's floor is flat and mostly unbroken. Now, Tycho's prominent rays of lighter material ejected by the impact, they stretch as long as 1,500 kilometers around the moon. Darker material was also kicked out and deposited immediately around the outside of the rim for about 100 or so kilometers, and that gives the crater a black eye appearance during and near full moon. The crater was named after 16th century Danish astronomer Tycho Brahe. There's a lovely pairing of the moon and Antares, one of the largest stars visible to the naked eye. As they rise together very late on Saturday night, April 9, they come closest at 2 o'clock in the morning on Monday. Antares has a radius larger than the orbit of Mars. That is big. When Venus is an evening star like it is now, we can anticipate attractive pairings with the crescent moon passing by each month. Did some of you see the beautiful pairing of the moon and Venus back on March 23? That was gorgeous. There's a repeat coming up on April 22 when a 2-day-old thin crescent moon slides midway between Venus and the Pleiades star cluster. On that same Saturday night, April 22, the Lyrids, the meteor shower, it peaks. Now, because the shower radiant is close to Vega, Alpha Lyrae, it's called the Lyrids, although its radiant is actually in Hercules. The thin crescent moon will set soon after sunset, so it won't interfere. The peak is around 9 p.m., just as the radiant is rising, but 17 minutes before the observing window opens. In other words, you can expect to see Lyrid meteors as soon as the sky darkens on that Saturday evening. You can expect to see 10 or more per hour, and I have found some predictions on some websites that were a bit more optimistic, supposing 20 or so. Now, after midnight, the eastern horizon faces the direction of our orbit, adding our orbital speed of 30 kilometers a second to the meteor's incoming speed of 18 kilometers a second, giving us the 5th fastest of the meteor showers. The Lyrids have the potential of producing long trails. According to Don Mackholtz, who writes for Earth Sky website, he said around 1 out of 4 Lyrids leave a glowing trail of ionized gas that can last a few seconds after the meteor has passed. 1 out of 4, I hope he's right. That would be amazing. The meteors come from debris shed by a long period comet discovered in 1861 by Alfred Thatcher. Comet Thatcher has a 415-year orbital period, so its next perihelion won't come until 2276. Now, this shower has the oldest recorded observations dating back to Chinese accounts from 2,700 years ago. Now, let's check out the planets, starting with the inner solar system. Each dot represents a day. Mercury reaches greatest eastern elongation from the Sun on April 11 on its way to inferior conjunction on May 1. Throughout the month, Earth is orbiting away from Mars while Venus draws ever closer on its way to its own inferior conjunction in a few months. You have a great chance to spot elusive Mercury on the evening of Tuesday, April 11, just 6 days from today, when the little world will be 20 degrees east of the sun. You should have no difficulty spotting it in binoculars after you wait for the sun to set. Once you know its location, you can find it naked eye. And you don't really have to wait until next week. You can try any clear evening. In fact, I heard on the way here that we're going to have clear weekend. This coming weekend should not be like today. It should dry out, and with any luck, we'll have clear skies, and you can start searching and finding Mercury as early as this weekend. You might detect its phase under very high magnification if the air is steady. At least Stellarium can do it. Venus is already high in the west after sunset, right? And it will continue to climb all month. Here we see it at 10:40 p.m. each night, climbing higher as the background stars sink in the west. Venus will reach its furthest point east of the sun on June the 4th. Now, as Venus approaches us, its apparent size and brightness will increase, while its phase decreases from 3/4 illuminated tonight down to 2/3 by month's end. And when this clip finishes, when it reaches May 2, there we see 2/3 illuminated. On April 11, that's the evening you're out spotting Mercury at its highest. Take a moment also to look up here and notice how beautiful Venus is right next to the glittering Pleiades. They make a great grouping, and together they make a great photo opportunity. Here we see them framed in a typical DSLR with a 300mm lens, suitable for your living room. Well, maybe not that big, but you know. It's springtime here, but fall for the Curiosity rover on Mars. In January and February, the rover took these stunning pictures of crepuscular rays shining through clouds at sunset. To get a good look at Mars from your backyard, or at least a look at it, look for a red dot about halfway up the western sky after dark. Here we see Mars's position at 10 p.m. throughout the month. Mars will travel east, up through the Gemini twins, while the background of stars sinks lower to the west. While sliding to the east, Mars comes particularly close to Epsilon Geminorum on Friday, April 14. At the start of astronomical twilight, the two are 13 arc minutes apart. Mars is only 6 arc seconds wide on the 14th. About the only thing April 2023 isn't good for is the outer solar system. Jupiter and Uranus are hiding from us behind the sun all month. And even Neptune, when it rises in the east, is so close to the sun's rising that dawn's twilight will wash it out. That leaves us with just a couple of pre-dawn hours with Saturn and a shot at Pluto for those with really big telescopes. If you get up before 5 in the morning in the last week of April, you can catch Saturn rising during astronomical twilight. The planet is located in Aquarius, and you will need strong magnification to examine the planet and its rings this early in its 2023 apparition, when its apparent size, including rings, is around 38 arc seconds. And if you do get a good look at the planet in your telescope, you'll notice that we are close to crossing the plane of its rings, which occurs every 15 years. We'll see the rings edge on in March 2025 as we pass south of the Saturn's equator and ring plane. And that's all I got for tonight. Are there any questions? Any questions in the room? How about online?
We have several questions online. First, I'd like to say that Kyle Gantz and Jack Mayer say hello, and we're watching online. We also have a question from Zapfan, who has a point. If you visit Sweden, you can visit Tycho Brahe's island haven. Some of his instruments have been redesigned, but his castle is gone. Tariq Al-Hamrani has two questions. So his first is, so this is for the Northern Hemisphere? What about the Southern Hemisphere? And his second question is, also, me being in Northern Hemisphere, will the sky be different from my latitude, 25 degrees north, than others who are much farther, much further in north?
Yeah, so I can definitely work on the second question. I did not study the sky for the month of April in the Southern Hemisphere, but I can tell you that you can see the same planets. You'll see the moon slide between Venus and the Pleiades. I think you should be able to see that. The Pleiades can be seen all over the world. Being close to the equator, it's visible in all continents. So I think some of these highlights I may have mentioned, the ones involving planets, yes, of course, the sun. If we do get auroras in the Northern Hemisphere, you get the exact same thing in the Southern Hemisphere, I believe. I believe that they're mirrors of each other. But I'm not 100% clear on that. I say that with a little bit of uncertainty. But I would imagine most of the other highlights that I talked about, seeing Saturn crossing the ring plane in a couple of years, yes, that's visible from the south as well. Now, the second question, remind me again? Further south, yes, of course. The further south you are, the higher the planets will appear. So I would imagine Mercury will be even higher up the further south you go. I'm pretty sure about that. But not 100%. A lot of the stars that you can see at 25 degrees, looking at the southern horizon, looking at the lowest stars you can see, are a lot more than what we can see up here at 40 degrees. So you have a much richer field of stars. You'll see more constellations. You can see further south than we can up here. So if we can see it, you can, and chances are you can see a bit more. I hope that answers your question.
Thanks, and that's all the questions we have online at this moment.
Very good. Okay, what I can do is bring up Frank's, and then you can introduce them.
Okay. We're going to go to a short break, and we'll be right back with Frank's presentation.
We can check the sound from here. You okay to go ahead? Okay, well, good evening. So it's always fun to be here talking about some aspect of astronomy. In this case, aurora forecasting, sort of that season with increasing solar activity. So I just put in, I carefully titled it Some Perspectives. That means I can choose what perspectives I decide to talk about. So you'll see what I mean. So let's get on here and a bit of an outline. And so I'll start off with a bit of a cause of aurora. I'll skip a lot of details. I know it's a huge subject, and so I will try to minimize some details and maximize some other details. Causes of aurora is basically the sun, but sun causes a solar wind to come toward Earth and affect Earth's magnetosphere. So I just put in one picture of a solar disturbance. In this case here, you see the upper right picture. Nice big disturbance leaving the sun. And the solar wind, instead of thinking of it as a wind that blows directly from the sun toward the Earth, think of it as a huge whirling plasma with mixed up magnetic fields, and it's a big spiral away from the sun. And any disturbance on the sun at any particular location may or may not be facing the Earth, or by the time the disturbance reaches the Earth, it may or may not be so-called geo-effective. So there's a huge amount of solar activity that I decided to leave out, from sunspots to flares, major flares, to coronal mass ejections, to coronal holes that I'll just mention briefly in passing. So the main point ought to be that the solar wind magnetic field has to couple with the Earth's magnetic field in order for energy and particles, charged particles in that disturbance in the solar wind to enter Earth's magnetic field and affect the atmosphere and cause glowing light. So those disturbances happen when the solar wind's magnetic field is oriented carefully to couple with Earth's magnetic field. So I threw in a couple of illustrations to illustrate that. There's some other details that are related to chemistry, which I decided to leave out about the interesting fluorescence of the Earth's atmosphere, but we don't need to go into that too much. So you saw this graph already. Sunspots are a huge impact, and so it's just worthwhile to mention that increasing solar activity right now this year is causing increasing chance for aurora in general. And so I put in a few cartoons here to illustrate increasing complexity of the Earth's magnetic field. So if you start with the upper left and you say a cartoon diagram shows a dipole magnet, that's a quick picture of the Earth's magnetic field. And then more complexity, when you look at it on the right, solar wind's magnetic field is blasting into the Earth and causing some interaction. And of course, in the bottom, there's quite a bit more interactions visible, and didn't want to explain them all. The main point, as I said, is that when the solar wind interacts just right with the Earth's magnetic field, then we get the energetic particles in the disturbance that's in the solar wind pouring into the Earth's magnetic field. And so, huge amount of detail. I decided to skip it all and just say that when that happens, we get some chance for aurora. And the point is to forecast it. So most of the presentation here is based on government forecasts of aurora. So you'll see what I mean. I said most of it, and I have my own forecasting technique at the end. So I just had many complexities, and here's another illustration, maybe more colorful, of the solar wind interacting with the Earth's magnetic field. And it has to happen just the right way when magnetic field of the solar wind becomes negative oriented or southward oriented. So I said it's basically all predictions are based on the government forecasts, and they come from the Space Weather Prediction Center. So you may have heard of it, may not. I'll show quite a few illustrations from it. The main reason I mention this is because almost every app and website I've seen that tries to forecast aurora bases on predictions from Space Weather Prediction Center. So that's what I'm using here. So that's fine. It's worthwhile to keep in mind some complexities here. And the KP index, KP is what I see quoted most often. There are several problems with using that as a forecast technique. It's not really very good because it's a measure of the planetary activity, not the local activity. So you can pull up information about more local magnetometers, such as Boulder, Colorado, or some spots in northern Canada, and get a better picture than the global average, which is what the KP is. And the other detail to keep in mind that KP is a 3-hour average of the average magnetic variations. So if you get an aurora that's, say, blasts up for, say, half an hour or 15 minutes, it may or may not show up in that 3-hour index. So those are some little faults to keep in mind, or imperfections. But meanwhile, the KP index is used quite a bit. And so you see graphs like this that show it every 3 hours for typically for a 3-day or sometimes a 24-hour back period. So this is a recent screenshot. And so you see it fluctuates every few hours from 2 to 4, basically, most of the time, typically. Interestingly, a couple of years ago when we were at the quiet period of the solar maximum that you saw in the sunspot diagram that both Arnold and I showed, pretty often this KP index was 0 or 1 for quite a long time. So we're entering busier times for magnetic interactions that may cause aurora. Despite the imperfections that I mentioned, KP index is used pretty often, and as just as a very general guideline, the pictures are intended to show KP3 on the left and KP5 in the middle and KP7. And so the auroral oval pictured in these auroral oval forecast predictions show KP3 causing auroral oval to be fairly well north of the Great Lakes area on the left, and KP5 near the Great Lakes, and KP7 not only over or south of the Great Lakes in the image on the right, but also quite a bit more intense. So the red means a higher chance for aurora to be seen underneath that auroral oval. So that's just a very brief thumbnail sketch of the difference between KP3, KP5, and KP7. So although I don't like to use them, and I say a few negative things about using the KP, including this comment that it's only quasi-helpful, it is used in widespread use for aurora forecasting, a little bit imprecisely in my opinion. So here's a question: when you see KP index was 4, 5, or 6, or 7 for the past 3-hour period, does that mean aurora is active in your sky? And for how long? And I mentioned the problem of aurora becoming pretty bright for maybe 15 minutes. Does that affect the 3-hour index? These are just some of the imperfections you have to deal with when you interpret the KP index. And the problem I've seen in the past 10 years is that whenever we see KP index of 5 or 6, I see some photographs show up on websites like spaceweather.com or others. I think of them as photographic aurora. And if I've seen a few of them as a visible aurora, it's just a puny little, tiny little, barely visible aurora. So, so I think the KP index is a little bit misleading, but that is the best forecast parameter that's being used widely. So that's what we're working on. So I just wanted to point out those little imperfections. So I just put in an example here. Suppose the time is 9:30 p.m. And so it's UTC 0130, and the latest KP index was 5. And so that means it was for the 3-hour period ended at 8 p.m. And so KP5 is fairly significant. It indicates minor geomagnetic storm conditions and very disturbed geomagnetic field. But what use is that for forecasting, or what does it tell you about what will happen now if you go outside now, or 1 hour from now if you're going to drive somewhere to a dark site? So is it any use? Maybe, maybe not. Anybody want to guess? If not, just advance to the next slide. So, okay. So to answer that question, I would need some more details about the solar wind. I would want to know what's the magnetic field strength and orientation. So remember, I tried to point out very briefly that the main impact of the solar wind that we need to be concerned about is whether it interacts with Earth's magnetic field or not. And it does when it's south pointing. So most of the time at normal equilibrium conditions, quiet conditions you could call it, the solar wind is oriented north pointing. But when it's got all these disturbances in it from the solar disturbances that cause magnetic field disturbances in solar wind, it could become south pointing. And when that happens, it's set to couple with the Earth's magnetic field and allow all that energy in that whirling plasma to pour into Earth's magnetic field down the field lines into the atmosphere and cause glowing light. But I also need to know the speed and density of a solar wind. I think those are critical to understand to try to forecast the whether or not there'll be any aurora when KP5 seems to be sounds pretty interesting. And so I'll just briefly mention there's quite a bit more than a couple of satellites, but these 2 satellites were sent to sit in the L1 Lagrangian point, sort of pictured on the right here. L1 Lagrangian point is where they're sort of stationary relative to the Earth. So there's sunward of the Earth, and they sit there more or less. They actually sit in a little halo orbit, as you can see in the lower left with that picture of the EST spacecraft. But the point is, those 2 spacecraft are measuring solar wind. That's their job, that's their intention, and they're setting back data. we can interpret full time because it's publicly available. So the ACE and Discover are the main satellites whose data I'm using here. So here's an example of real-time solar wind data that we can get from the website, Space Weather Prediction Center at NOAA.gov, and some other products. I'll point out a few of these, but most of them come from SWPC. So the point here is, excuse me, the point here is you see BT, or the total magnetic field strength, marked off in that black line at the top. And it doesn't really show up here. Maybe it does. Maybe I can get it here. BT. And the BZ is the vertical component. If you think of the solar wind coordinates in Cartesian coordinates with X, Y in a horizontal plane and the Z coordinate, and the vertical pointing up or down. The BZ is pointing upward, as you see it positive here, and then it's a sort of normal situation where it doesn't really interact with Earth's magnetic field. But when it becomes southward pointing, or BZ becomes negative, or the Z component becomes negative of that magnetic field, then it's set to couple with the Earth's magnetic field. So we're really looking for BZ to be negative if there's going to be any chance for aurora. And so here's this plot for a one-day period, and this is a fairly recent situation. There probably I copied it yesterday or a couple days ago when I was setting up the presentation, but it's a very good illustration because BT is not very strong. I really want it to be well above 10 nanoteslas on this graph before there's any real chance for aurora. And I want BZ to be negative, about negative 10 or stronger to be any real significant chance for aurora. So here you see it diddy-bopping around, just fluctuating around, not really strongly positive, not strongly negative, just sort of interestingly fluctuating quite a bit. And it has been a disturbed condition for the past few days. That's fine. So the other detail I want to look at is density. So the solar wind density is a straight line here, more or less, approximately. And the speed, generally I use 500 kilometers per second as a rough guideline, where if it's faster than 500 kilometers per second and some other factors are in place, yes, there's a good chance for it to cause aurora if it's going to do that. And if it's slower than 500, it won't really. So this is an interesting period, the past few days, where speed is genuinely above 500 kilometers per second. And BZ has been negative. So anyway, that's just an illustration of the real-time solar wind data. I think I have a couple more. That was Discover, I believe. And this one, I think, is it ACE? No, it's Discover again. Okay, so I threw in the example for March 23 and 24. And so just out of curiosity, did anybody here see that bright aurora on that Thursday night? Okay, maybe not, maybe. So the point here is it became pretty darn interesting on the night of March 23rd, around 11 p.m. Local time, and there was a big aurora outburst. It was quite visible even from my light polluted yard where I live. But the point here is I put in the arrows to mark off the time of March 23 to March 24. And it's a very interesting, it's a very good example that I put up here to illustrate how I use the data to forecast the aurora. So here, it doesn't show up so well on this graph, but I have a better one. But look how high BT became. It became up around 20 nanoteslas. That's where I want it to be. And the BZ became sharply negative after that. And density graph showed classic shock wave. So a shock of increasing particle density hit the Earth's magnetic field, or actually hit the location where those spacecraft are, and the Earth about half an hour later, roughly. That's what's a great picture for an aurora. Speed, it's already well above 500 kilometers per second, or it's pretty close to it. So certainly within the guideline that I think is pretty reasonable for causing aurora. So classic picture right there for that particular period, which is a rare aurora. So recall this, I showed you all this earlier. So I showed you this stuff here down to here, and I said, what about now or 1 hour from now? And so now that I've pointed out that we need to be aware of the solar wind information, I want to know what is the latest BT, BZ, and solar wind speed. Remember, BT is the total magnetic field strength, and BZ is a Z component. And B, just so you know, is in physics, is the capital B is used to represent the magnetic field. So BT and BZ and solar wind speed, that's what I want to know. So I can just open this website, swpc.noaa.gov. I mentioned this one as a classic reference website because all the others that I've seen, all the apps and websites use data from here, use the exact same data that's here or older. So this is, open up that and it shows at a glance, current solar wind speed, current BT, current BZ, is it negative or positive and how much? and furthermore, the flux. And I'll mention the solar flux later end of the presentation. So all this is available at a glance because it's important. So fine. So now I'll show a few online resources. I didn't try to list all the websites and all the apps. I just picked out a couple that I was able to successfully download the trial on my iPad, although I couldn't get one of them to open and work. But it doesn't matter because they all show the same thing. All the data I just showed you is what they show. So they provide links to the latest KP, forecast KP, and it's almost all from NOAA SWPC. And some apps even provide the latest solar wind info. And by that, I mean that some apps don't do that. So I really think you need to know that, or at least I need to. Now I understand some people in the room are not physicists, chemists, and say, never mind all this garbage nonsense about magnetic field. Just tell me, is there going to be aurora or not? And that's the popularity of the app, and they try to do that. So okay, I understand that. So fair enough. Back to the SWPC website. You click on dashboards. You can click on space weather enthusiasts or click on aurora and get quite a lot of information. I'll show a few examples. So here's a KP index for the past 3 days. I showed this earlier, I think. Maybe I did, maybe I didn't, but shows quite a lot of detail. If there's a major solar flare, it'll show up right here. If there's an X-class flare, this graph will jump up to into the X range. And it's pretty significant because it may cause a solar disturbance that may be in a solar wind that, if it's oriented just correctly, to come toward the Earth and have a negative pointed magnetic field. Everything else is just correct. In that big, huge spiral of solar wind that's flowing away from the sun, may or may not reach the Earth. All their computer forecasts may indicate there'll be a big disturbance, and it may just miss the Earth, or it may hit it and cause a big impact. We don't know, and forecasts are not really very good. So this is why I'm going to do a last-minute forecasting based on numbers I can find on this website or some others. Anyway, just wanted to illustrate. That's one detail you can get. Here's another detail you can get. Three-day forecast for KP index. I've mentioned a few times, it's not 100% accurate. However, all the websites and apps I looked at take these numbers and project them as if it's gospel. So, okay, fine, that's one way to do it, because the non-physicists will say, just tell me, is it going to be aurora or not? And is the KP index going to be 5 or 6? That's one way to, it's a very rough approximation just to look at these numbers and say, okay, go with that. So anyway, that's available on that website, or any website, really. Here's another product you can get from there, an ST Aurora forecast. Slight complication, you can get a half-hour forecast, and half-hour forecasts are fine. They're pretty good because whatever is measured at those spacecraft that I mentioned will flow in the solar wind, which is approximately half-hour upstream from the Earth. So whatever is real-time being measured at the spacecraft will impact Earth roughly half an hour later, depending on the speed of the solar wind. So fine, a half-hour forecast, aurora forecast is fine, but I've found this things can change in half an hour. So it just can suddenly turn to red when it suddenly becomes aware somehow that aurora is developing faster than predicted. That's okay. Me being a meteorologist for the past 20 years, I can assure you that not all forecast models are correct, and things can change. And you can see a forecast for clear skies, cloudy skies, rain, thunderstorms, and models are imperfect, forecasters are imperfect. Things can change in half an hour, right? So, okay, fair enough. It's not perfect, but I don't tend to rely on it too much. Oh, there was one detail I wanted to point out while I had that. Nope, back up. We'll be back up here. Oh, neat. I think, oh yeah, so I put a note in the top right corner because I'll refer to it later. One other detail I want to look at, it's actually marked off. You may be able to read it, may not. Hemispheric power index is marked off here. It's predicted or it's indicated. I think here, I can barely see it. It's around 33 gigawatts. And for a strong aurora or a reasonable aurora, I want it to be around 40 gigawatts. So skipping a lot of details, it's just the amount of energy being dumped into the atmosphere by the aurora. Or at least by the solar wind particles pouring into the Earth's magnetic field. Okay, I just wanted to point that out. Another, you can get more predictions of solar wind prediction, and it's pretty darn interesting, and it's actually a movie. If you click on here, you'll see it scroll through here, and stereo A and stereo B are two other, but the point here is it's got its own forecast of the plasma, of the density and speed of the solar wind for next several days. So that's pretty handy, although again, it's not perfect. But when you see a big hump coming where it jumps up, that would be a detail to watch out, that there may be a good chance for aurora if everything else is lined up. I said they're not, websites are not all really good. So there are some that are a little bit imperfect, such as this one. I got this today. I said, what the heck's going on here? What's this 7? And what is this number that they're getting? Where are they getting it from? Where is it currently 7? Is that the KP index? I don't think so, because the current KP index this morning is 3. So where are they getting these numbers, and what the heck do the numbers mean? So these guys here, to scroll up higher up here, it's our auroraforecast.com, or it was the same one that Arnold mentioned. And so what the heck's going on here? So my point here is watch out, be careful. Decide what you're looking at. Anyway, back to my preference, what I decided, I told you it's my perspectives. And so my perspective here is to look at the solar wind for the past 24 hours, see what I think if there'll be any reasonable chance for aurora. And yes, I mentioned earlier, BZ is negative. BT is pretty weak, actually. It's not very strong, and BZ is not really strongly negative, and speed is way up there. It's around 500 kilometers per second. I don't really see any density shock wave. So despite all this conditions being quite buzzing around and quite hopping around for the past 24 hours, I wouldn't, it's not any chance for aurora, especially not while KP is fairly low. And here's past 30 days, and I don't think there's anything I wanted to point out here that I didn't point out earlier. I pointed out this interesting period here, so I think I'll skip that. Just to point out, you can get the past 30 days, or quite a lot of past data, but the past 30 days is very useful for considering the past month, what's happening. And I'll show you what I mean when I talk about coronal holes. In that case, the speed, oops, I should back up a little bit. If so, I should point out just in that passing that the speed was pretty fast here around end of March. So if I think I have a picture of this again later. So just one detail to point out, solar wind speed was pretty high last few days of March. Anyway, so some other websites give nicer, easier to read illustrations. So another one of these websites is a more readable version of this same data that's from the SWPC. It's just plotted for the past 3 days. It's just a nicer, easier to read, maybe, interpretation. You see, speed is more delineated here, and can you see it more information at a glance. So just to say that there are some other websites that have good presentations of data. So I picked this KP index of 1 of April 1st, and didn't want to go into too much detail that I haven't already explained. Didn't want to go on too long about a whole lot of details, so I think I'll just skip that. I think that was what I showed you earlier, that information. Oh yeah, I wanted to show out this detail here because I'll go back to this as a very good example of a very rare situation that occurred and why I didn't expect it. Why I thought, forget about your aurora forecast for that Thursday night. And that was because earlier in the daytime, these guys had this forecast out showing pretty high numbers for the Thursday night. So I sent an email to the Toronto Centre Forum saying there may be some chance for aurora tonight. However, I decided around sunset, pretty slim chance because it began earlier than expected. So already in the afternoon of March 23rd, KP index had jumped up to 7. So quite a significant magnetic storm is already underway in the afternoon. Whenever I see that, I figure it may last a few hours, may last 3 or 4 or 5 hours. So by the time sunset comes, it'll be diminishing. It'll be a waste of time to even worry about it. However, it was clear that night, so I went out anyway. Stargazing, I had my own list of observations to do, but I was surprised because it did blast up, continue on. So it was a long-lived geomagnetic storm. So it's quite a rare situation, but it just shows the advantage of looking at past data. I want to know what happened hours earlier in order to decide what will happen in the future. In this case, I decided it was pretty darn active in the hours earlier, and I decided to write it off for the next few hours. Anyway, so that's one good example of a blown forecast, but the value of looking at previous data. So just as another illustration of some websites that have some pretty good data presentation, the solar wind density, remember I mentioned it, shockwave, it shows up really clearly here. shows it really sharply, and this is the Thursday afternoon. Shock wave came, and then I showed you the KP 7 or 8 that blasted up after that. That's density. This one is a total magnetic field. It jumped up to about 20. That's where I like it to be for significant aurora. The BZ went strongly negative, and it's around -10 or lower, went to around -20. So you may remember I mentioned, or I think I have a summary at the end pointing out, I wanted to be around the area of -10. And just as I mentioned earlier, right about now, this past couple of days, it's been around -3, maybe -5, and don't really worry about it too much. But -10, that turned into a pretty good aurora. Here's a detail I wanted to point out. Taking the total break from all of what I showed you earlier, when you have coronal holes, because they tend to repeat on a 27-day rotation cycle of the sun, they last for several months generally, or they can last for several months. This is one way of forecasting that I used about 30 years ago, and I decided in the past couple of decades that solar activity is decreasing. There's quite a lot of evidence I'm aware of for that, and so I really thought that what happened a couple of weeks ago would never happen again in my lifetime, but it did, of course. But so anyway, your coronal holes illustrated here. Nice, colorful, pretty picture that doesn't show you much unless I tell you that this is the coronal hole, and this is another coronal hole and another particular wavelength. So details don't matter so much. That they are big, huge coronal holes, and they allow a fast solar wind to stream out away from them. And as I said, if it's Earth directed and oriented just correctly, it could have a big impact on Earth. Solar flux, I watched solar flux very carefully, and solar flux goes approximately in parallel with the sunspot cycle. And so it's increasing quite a bit lately. So the numbers are around 150 to 175 this past month or so. They've been as low as 75, and that's significant because I'll show you probably the next slide here. Maybe not this one here, but is that mentioned here? What was I going to show you here? I think I'll just skip that. I think I showed you that earlier, and I mentioned a few details, so I think I'll skip that. So this is a piece of paper I pulled out from my notebook about 30 years ago. This is what I used to do before there's any solar wind data coming from satellites. Before those satellites were launched, I listened to shortwave radio. I copied down these numbers every day, the AP index, daily AP index, Boulder ANX, and a solar flux. And I put it down on a sheet of paper, and I graphed it every day. And you may be able to see this little graph here. So this was solar flux increasing at this particular time of this month in October. And the chart range is 154 to 272 solar flux units. And so the point is that's much higher than it is right now, around 175. So it has been much stronger in the past. So even though right now I see solar flux increasing, it's still tiny compared to what it was 30 years ago. But this is what I did 30 years ago. And some of you may remember in the early 1990s, we had a lot of strong, powerful aurora. So in this case here, using the method of saying coronal holes repeat every month, and we use that as a forecast method. So the point being that solar flux increased here, probably due to coronal hole at this time of this month, coincided with a strong AP index or strong geomagnetic activity here. I put some asterisks on here which marked off major solar flares that were also reported on the radio. This is even before internet existed, I think. But anyway, this is what I did 30 years ago. So I use this method. And so I think I have one slide. Oh, I know what I was going to show you. I know what I was going to show. To repeat it again, you see this strong solar wind speed here, which I mentioned a couple times already, but was over 600 kilometers per second around the last few days of March. So if this is due to a coronal hole effect, then don't be too surprised if that repeats again around the last week of April. And so in this case, using the coronal holes, just based on what I did 30 years ago, I don't really care what the BZ is or how fast the solar wind is or how strong the magnetic field is, because I didn't care 30 years ago because that information was not available. I just said a recurring coronal hole coincided with strong geomagnetic activity. And so I wouldn't be too surprised if there's some increasing geomagnetic activity and high solar wind speed, again, around the last week of April. So there's one prediction. So I said it's totally different from using the government-issued KP index. So I think that's all I wanted to show you. it's almost, I finished off with a few slides of predicting some forms of aurora, so I might as well finish off with that. So initially it begins as a homogeneous arc, and you may be able to pick out here a light green band here. It's another example of a photographic aurora because it was visually white, and this was from March 23rd. I went to an aurora viewing spot and I decided I'll watch for it to develop here. I sat for 15 minutes maybe, and I thought, not much happening, but there's a very weak homogeneous arc, and it may blast up, but I'm not going to waste time because I already wrote it off. Remember, I saw the strong geomagnetic storm earlier in the daytime, and I said, it's finished, it's not going to do much now. So I watched this and nothing was happening, so went home, do some more observing. Homogeneous arc, so typically when you see that, it may develop after an hour or so into rays and curtains. So here you see some rays or curtains blasting up, developing, and becoming quite energetic. And this may last 15 or 20 minutes, or it may last for an hour. On March 23rd, that Thursday night lasted around 15 to 20 minutes, and it diminished a little bit. But I have seen it in the past when there were strong auroras 30 years ago, go on for an hour or two, strong blazing curtains and rays like this. But anyway, that's following the homogeneous arc, and after it's diminished a little bit, typically you see sheets shimmering across the sky. That may last a whole rest of the night, or it may last an hour and gradually diminish. This one right here is from that Thursday night and Friday morning. You may be able to pick out a hint of some color in the sky here, but from my yard. But these ones from 30 years ago were pretty strong with color, intense color, and they were pretty bright. I haven't mentioned what causes the color because it's some chemistry related to the fluorescence of the upper atmosphere. Don't want to get too distracted on that. The point is, this may persist for a little while, so you may see that, and then it may progress to some other forms. And I've got a nice little picture here from the Observer's Handbook. But you may see a corona overhead, and it's sort of a nice illustration you have over right here. But it's basically when rays converge directly overhead, or actually high in the south, a little south of zenith. You may say it's pretty darn weird to see pulsating spots high in the sky, especially 3 or 4 in the morning after a major aurora display. You see aurora has all finished, and you look up in the sky and you see flash, 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 flash of faint gray light. It's not very bright. See what the heck's going on here? But it's okay. Frank just told you that there's pulsating spots as one of the aurora forms. And you may see flames that are shooting up, and a good illustration here again, you see flames popping up every few seconds from the horizon, and there's generally not very bright. And then sunrise, because it's pretty late in the night by that time. So in summary, I really prefer to see the big picture rather than look at numbers like the KP index only. And I really want to see some numbers I pointed out already. They're summarized right here for what I want to see in a solar wind before I think there's any reasonable chance for aurora. So all this stuff has to happen. And I mentioned also if it's following a density shock wave like illustrated for the March 23rd event, that's pretty handy too. That's a very good forecast feature to see. And I told you my own method, which I wrote off. I thought I'll never see again in my life, but this past event may be a resurgence of the major coronal hole stream method forecasting auroras every month if they occur, regardless of what all the numbers are. So anyway, that's that, and I've finished off here. Just listed some resources that are pretty handy, and I'm finished. So thank you for your time. If there's any questions, I'll try to answer some.
So we have one question from Kyle, who asks, is this available with hourly data, the data from the aurora? I sometimes image the sun and would love to match the data with the time I was imaging.
The answer is yes, but not hourly. It's minute data. It's 1 minute data. So if you were to look closely at those graphs that I showed for data of a solar wind measured by a spacecraft, they are 1 minute data. So they fluctuate on timescales of 1 minute. And that's pretty high resolution, in my opinion. It's pretty handy because some solar features may be aware of that someone may photograph may last only a few minutes. And you may see them visually too if you're looking with, say, an H-alpha filter. Some of you may have seen solar flares erupting. pretty rare thing to see visually, but I saw it with a little Coronado maybe 20 years ago. But it's really neat to see a solar flare erupting. For a few minutes, you see it snaking across a bit of a sun's surface. And so we're talking about a time scale of a few minutes. So the questioner may be talking about imaging the sun for some feature that lasts a few minutes. And so the answer is yes, but the data I showed are solar wind data measured at the location of those spacecraft. And time from the sun to reach the Earth is generally 2 or 3 days. And so the data that I showed is not really coinciding with what you see in the sun. It's what's being measured at the yellow one Lagrangian point, about a half hour upwind of Earth, you could say. So it doesn't really coincide with the sun. Solar data is a total different kettle of fish. Arnold hinted at some information. I decided to skip it because it's a huge, huge kettle of fish. But there is a lot of solar data available, but it's not what I showed. So it's an interesting question. 1 minute data is available, but it doesn't really coincide with what you can image on the sun.
Thank you. And that's our questions for this evening.
Any questions in the room?
Frank, when I finished my talk, there was a question about what do we see down south? And I supposed, and I'd like to know if I was right, I said that if we get an aurora in the northern hemisphere, you're going to see one in the southern hemisphere, and they will be like similar. Was that right?
Yes, according to textbooks, it is quite correct that the northern and southern auroral ovals are mirror images of each other. I'm not totally sure, and that's a good question to research, because there are some anomalies in the Earth's magnetic field, such as the so-called South Atlantic anomaly, which is a very interesting study by itself. So there are some imperfections in that mirror image idea, but that was the old textbook idea from even 50 years ago when aurora was studied quite extensively. It's tricky even to try to compare Earth orbiting satellites or even GOES imagery, or the old-fashioned, what we call them, space shuttle imagery, because by the time they reach halfway around the world, it's a good 45 minutes later. So that's not really comparable. But it's a very interesting question to research, but I don't know, it's a good question to discuss. Anybody have any discussion like Chris?
So the auroral ovals are centered around the Earth's magnetic poles rather than the Earth's axis of rotation poles. So if the magnetic pole in the northern hemisphere is, say, in northern Canada, sort of south on our side, the southern magnetic pole is going to be offset on the other hemisphere. If we're in the eastern hemisphere, they'd be on the western hemisphere, so that the direction of the ovals will be offset in that sense. So it wouldn't be quite a mirror in that way. It might be 12 hours later that it matched, in other words.
Okay, good point. So it's not a mirror image geographically, but magnetically it probably is. Good point. Yeah, it's an interesting question.
Good. More questions? Oh, Arnold.
You have a fist fight.
Okay. Hey, Frank. I was wondering how much of a risk does the aurora phenomenon or related phenomenon have for satellites, power lines, computer chips, things like that? I have heard that for large corona outbursts that they've closed down satellites and shut them down to shield them against hazards posed by the sun. Are these associated?
Yep, 100%. Good question. I decided to leave it out. That's such a big field. I actually started off, I threw out a lot of slides, but one was showing the impact of why does aurora matter. And the aurora forecasting is only one trivial part of the geomagnetic effects. So they influence power lines and pipelines. They induce currents in them. Back in the first huge aurora of the 1990s was 1989, and it blew out a lot of transformer equipment in Quebec, long transmission power lines. And it convinced a lot of power companies that they got to upgrade their equipment to be resistant to that sort of problem. This happened elsewhere in the past, but that's also trivial compared to effect on expensive satellites. Some have been conked out by it. A good example of the increasing, a recent launch of, what do you call those pesky satellites? Yeah, Sterling. So I launched, a set that got launched had got scrapped and got burned up in the atmosphere because it couldn't be raised to high enough orbit in time, and they reached increasing density. So I thought in that case, good, we hope for more geomagnetic storms that will take those suckers out. But the point is, that's trivial too. I think the reason that the U.S. government made about 10 years ago made Space Weather Prediction Center, and it used to be called Space Environment Center, made it a part of NOAA, Department of Commerce, because there's huge resources that they could lose. I didn't put up pictures of, you go on the website to see different effects. They've got pictures of farmers in their field using GPS to plow their fields, and other things that rely on GPS. And that's all trivial. If you put up a picture of a warship or something that the U.S. government spends big money on, not to mention a lot of things they have flying around and a lot of resources they have tied up that are really strongly dependent on geomagnetic storms. That's one huge thing. Another huge field I'm aware of is manned spaceflight. And that's a slight challenge, to put it mildly, for people expecting that they'll send men to Mars or people to Mars. I think I don't know any solution to it. Be interesting if anybody here has heard of any solution to it, but I think it's a mostly insurmountable challenge to how they'll deal with the risk of solar storms. And it's rumored that the Apollo astronauts were very, very lucky that they didn't get blasted out by a solar storm. They didn't even know about them. It was really only 1975 when I remember Skylab was orbiting, and it studied and discovered a lot of these interesting things that were unknown before then. So I'd say the U.S. government's huge resources that they have dependent on communications and stuff, and spaceflight, or human spaceflight, are probably the biggest consequences I'm aware of. But yes, expensive satellites get conked out or they're at risk. One of the SWPC's categories was for satellite operators, and they have, you can pull up some graphs and charts showing the satellite charging effect of the charged particles coming into the atmosphere, because it's always in flux, always changing. It's not zero, there's always some amount of charging going on. It's always influencing radio. It's always influencing, to some degree, communications, like aircraft try to fly across the pole. Sometimes they can't. Sometimes they have to make expensive detours around North Pole because of lots of communication. So there's a lot of expensive consequences due to geomagnetic storm effects. So short answer to your question, yes, hugely expensive problem, and aurora forecasting is just the most trivial aspect of it, but they're nice enough to put up information for what they call space weather enthusiasts and aurora watchers.
Thank you. Okay, any more questions for Frank? Very good. So, thank you very much, Frank. Very informative and detailed presentation, and I actually learned a few things myself. Even though I've been observing the aurora for a long time, I always relied on the KP index. Now I know better. Thank you very much. And also, I didn't have a chance to thank our previous speaker, Arnold. Great graphics and animations, really helpful and very well done. Thank you for coming to present to us. All right, so that concludes the speakers for this evening. I'll call on Tom Luton to take care of the announcements. And we're going to go to a short break. We'll be right back.
All right. Well, good evening, everyone. I would like to start by once again thanking our speakers. Thank you very much to Arnold, and thank you very much to Frank. And my apologies to John. We will get you scheduled in for some point in the future. So let's get on for the announcements. So, as Paul was saying earlier, we've got two types of meetings going on here at the Toronto Centre. You've just seen one of our recreational astronomy nights, and coming up in 2 weeks' time is going to be one of our speakers' nights. So, if you're watching us on YouTube Live, please say hello in the chat, enter some questions for the presenters, as others have already done. If you're a new member, please introduce yourself. And if you're coming to us from far, far outside the Toronto area, please let us know where you're coming from. So our next speaker's night is in 2 weeks, Wednesday, on the 19th of April. Dr. Haley M. Sapers, PhD, intraterrestrial to extraterrestrial, deep subsurface microbial communities and searching for life on Mars. That will be online only. You can watch that at our YouTube channel. Our next recreational astronomy night is the 3rd of May, 7:30 p.m. in person at the Science Center and online. Andy Beaton will be discussing the sky this month, and Clay Davies will be discussing telescope mirror making, a superb polish with a cheap but vile, slow, messy slurry. And we've also got one open slot. If you'd like to present something, please contact Paul Markov. Coming up at the DDO in the next little while, we have Sunday sun gazing on April the 9th, 12:30 p.m. You can register online. The links can be found at rascto.ca. Our next DDO Astronomy Speakers Night is Saturday, April 29th at 9 to 11 in person. Dr. Keir Rogers will be discussing a search for dark matter in the cosmic web. Again, registration links at rasto.ca. And then DDO Planetarium Day on Sunday, April 30th, 2 sessions, 1 p.m. to 2:30 p.m., and then 2:30 p.m. to 4 p.m. in person. Again, registration and links at raskto.ca. The CAO, our club observatory up in the Blue Mountains, is still closed until further notice because of road conditions. Fingers crossed that that resolves itself fairly shortly. We're hoping sometime this month. I don't know if you've heard about this, but yes, there is our first public stargazing event for the year at Millennium Square on the 28th of April, Friday, 6 p.m. to 11 p.m. Join us in our sponsor, Durham Skies, for an evening of free public stargazing along the North Shore of Lake Ontario at Millennium Square. Take a look at the moon and stars through our telescopes. We'll have some astronomy literature. We'll be available to ask questions. You can bring your own scope. We'll help give you a hand setting it up and working properly. Just a reminder, things are cooler down by the lake. We're still recommending that you wear masks. And please use the disinfectant we provide for our info booth. There will be a go, no-go decision made on Friday, April 28th for the weather. Please check our website before heading out. There will be Astronomy Day here at the Ontario Science Centre on Saturday, April 29th. Exact details are still being finalized. There will be a solar observing session. And on that note, I'd like to make an announcement. Our longtime Science Center contact and liaison, Rachel, has handed the reins over. And I'd like to introduce you to our new member of the connection with the Science Center. This is Emma, and we will be her problem going on for the next, hopefully, a long while. Welcome to the family, Emma. And also, regular solar observing will be starting up at the Science Center starting in June. Details to be announced. We're also looking for some folks to fill in some slots that are currently vacant. We are looking for an editor for Scope. So it's a bi-monthly publication that's distributed to all the members of the Toronto Centre. If you like to edit and write, please get in touch with myself or at volunteer@rastio.ca. We've also got some additional job posts that we're trying to fill. We're trying to find a new education and public outreach chair, a light pollution committee chair, and a volunteer committee chair, as well as a marketing committee chair. The Education and Public Outreach Committee is always looking for additional presenters, especially if you've got the equipment to assist with virtual star parties as a telescope camera operator. Just a reminder that to volunteer, you first must be a Toronto Centre member. Please contact myself at president@rastio.ca if you'd like to help. Just a little plug here for RASC membership. You can renew or sign up online at secure.rasc.ca, and gift memberships are available from the national office. Contact mempub@rasc.ca for more info. For those of you here in person, I'd like to invite you to join some of us for the meeting after the meeting. We meet at the Granite Brew Pub, corner of Eglinton and Mount Pleasant, 245 Eglinton Avenue East, if you want to plug that into your whatever app. Free underground parking. Entrance is off of Mount Pleasant Road, usually in the back room, but we've been moved around a bit. So when you come in the front door, take a look around. You'll probably spot us. And for everyone else here and online, I'd like to wish you all a very pleasant evening. I'd like to thank you all for joining us. Please follow us on all the forms of social media we've got listed here. If you liked what you've seen on YouTube, please like and subscribe and hit the notification bell. Be safe and keep looking up. Good night, everybody.